4.8 Antiderivatives. Antiderivatives. So definition. A function, let's spell that better, be nice. A function f, sorry, it's bad. Okay, a function f, capital F, is an antiderivative of little f on interval I if for every x in I f prime, capital F prime of x is equal to f of x. So this is the antiderivative of the little f function if I can take the derivative of this function and receive the original. So our job eventually is going to be able to try to find this function. In order to know that function is correct, we're going to find the function and we're going to quickly take the derivative to verify that is the function we were looking for. So, example. So we're kind of working backwards. Instead of taking the derivative, we're going to figure out. We're going to say, well, this is the derivative of something. Find what that function was. So, example. Find the antiderivative, and we're going to start. We're going to start small. So a. So little f of x is equal to 2x. B little f of x is equal to the cosine of x, and then c f of x is equal to 1 over x plus e of x. All right, so the solution here, we're going to find these antiderivatives. So this is the derivative of a particular function, so I need to see what function that was. So working backwards. So what was capital F of x? So what function do I take the derivative of in order to get 2x? So I think you guys probably have already seen it, that's x squared. And now all antiderivatives are going to have your function that you expect, and then we're also going to put a constant on the end of it. And the reason why is because the derivative of any constant is equal to 0. So like kind of an example of that would be, say, x squared plus 5, for instance. I know if I take the derivative of this function, I'm going to get this function. Or even like x squared plus 8. The derivative of this function would equal this function, or minus 8. So no matter what, there's a constant on the end of all these because the derivative of a constant is equal to 0. So then we can do a quick check. What is f prime? What's the derivative of this? Well, this is 2x plus 0, which is what we're looking for. So that's what this definition means. It means if I can take the derivative of the function I'm finding and get the other function back, then that's the antiderivative. All right, for B, capital F of x. What function do I take the derivative of to get cosine? No, it's the sine of x. And we plus c, because remember, there's always a constant here because the derivative of constant's equal to 0. Let's check. What is the derivative of that? Well, the derivative of the sine of x is the cosine of x, and the derivative of c is equal to 0. So that is the antiderivative. And for c, capital F of x. What function do you take the derivative of to get 1 over x? Well, that is the natural log of x. And what function do you take the derivative of this to get e to the x? Well, the derivative of e to the x gives you e to the x. And then, of course, plus c. And then we can do a quick check. What is f prime of x? Derivative of the natural log of x is 1 over x. The derivative of e to the x is e to the x. So boom, that one works as well. Now you're going to be pretty good at much of these because we've had so much work with derivatives that going backwards isn't going to be too bad. So I don't know if you've heard of what's called differential equations. Well, what we're actually going to do is we're going to do a differential equation right now. This is what I'd shoot for like day one of differential equations, and then we'd build on this a lot. But this is at its heart kind of what a differential equation is. So the idea is it says find the antiderivative of f of x, which is equal to 2x, that satisfies f of 0 is equal to 4. So we're going to find a particular. And what I mean by a particular means that instead of just a plus c, we're going to figure out what that c value is. We're going to find that exact c value. Okay, so the solution here is what I need to do is I need to find the antiderivative of a little f of x. Well, we already did that one. The antiderivative of 2x is x squared plus c. Now, so far what I know is this is the antiderivative, but it also has to satisfy f of 0 is equal to 4. So now we're going to determine c using f of 0 is equal to 4. So what I'm going to do is I'm going to plug in 0. So when I plug in 0, I'm going to have 0 squared plus c. And let me just erase it. I'm going to rewrite this. So f of 0 is equal to 4. Well, f of 0 would be 0 squared plus c is equal to 4. So that means c is equal to 4. So therefore, our antiderivative, our particular antiderivative, is f of x would be equal to x squared plus 4. And it has that, and it satisfies these. The derivative of it is equal to 2x, because this would be 2x plus 0. And when you plug in 0, you get 4 back. For some reason, I thought I had more examples than that. I just want to make sure. Yep. Okay. So we're going to do more of that, but we need some more background before we do it. All right. So that's right. Table 4.2. It's right in the chapter of chapter 4.8. Section 4.8, and this is just an antiderivative table, and unfortunately, you do need to memorize it. Well, what I'm going to do is I'm going to write down the ones that you need to memorize. So there's a couple of them that are not necessary because they just don't come up enough. So the one, this is going to be the power rule. So let me erase this. I'm going to write the function, and then it's going to be its antiderivative. So function. And then over here is going to be general antiderivative. All right, number one. This is called the power function, so x to the n. And its antiderivative is, well, it's opposite of what it's the inverse of what the derivative is. With the derivative, you would multiply by n, and then you would drop this thing. So its antiderivative means instead of this being n minus 1, it's going to be x to the n plus 1. It's going to be backwards. And instead of being multiplied by the power, it's not going to be divided by that power. So its antiderivative is x to the n plus 1 over n plus 1 plus c. And this is for n not equal to 1. Because when it is equal to, I'm sorry, not equal to 1, but not equal to negative 1. Because that's a logarithm. Number 2, sine of kx. So the antiderivative of the sine is minus the cosine of ax, so this would be minus the cosine of kx. Now remember, when you're taking derivatives, like if I had the sine of 3x, for instance, and I want to find the derivative with respect to that expression, this would be equal to the cosine of 3x, but then I'd have to multiply by the derivative of the inside, so you'd have to multiply by 3. Now, antiderivatives, instead of multiplying by that constant, we're now going to divide by that constant. So this 1 over k is actually divided by that 3. So if I say, so for instance, if I have, let's say I have the cosine of 3x, and I want to find its antiderivative, what function do I take the derivative of to equal this thing? So we're kind of, we're trying to determine this piece essentially, right? We're trying to find that piece because I need it to equal the cosine. So what I know is the derivative of the cosine is going to be equal to the sine. So this is going to be equal to the sine of 3x. Now when you take the derivative of the sine of 3x, you're going to get the cosine of 3x, but then you're going to get multiplied by 3. So you get a 3 here, but I'm not asking for a 3 here, I'm asking for a 1 here. So that's why I have to put this right here. So for instance, when I say the cosine of 3x, not 3x, I want kx, I want any number, so 3 is just one particular k. So the cosine of kx, well, its antiderivative is going to be 1 over that number times the sine of kx plus c. So this is kind of how we build it. Like the derivative of this thing is equal to this thing. So that's why we know that this is actually working. Now the reason why sine and cosine change sign is because the derivative of the cosine is negative sine. So the derivative of negative cosine would be positive sine. The secant squared of kx. Now the derivative of, well, what function do you take the derivative of to get the secant squared? Well, you know it's going to be the tangent squared, not tangent squared, but the tangent of kx. But when you take derivatives, you would multiply by the k, so when you take antiderivatives, you're going to divide by that k. And then, of course, plus c. Cosecant squared kx. Well, you know the derivative of the tangent is secant squared, so this, of course, is going to be cotangent of kx. Now, remember, the derivative of the cotangent is negative, so in order to make this positive, I have to change this sign, and then instead of multiplying by k, I have to divide by k for antiderivatives. 6 secant kx tangent kx. Well, we know the derivative, the function that gives us secant tangent is the secant function, so you know that this is going to be the secant of kx plus c. Now remember, when I take the derivative, you'd have a multiplication by k here, so in order to get rid of that multiplication of k, I have to have a 1 over k here to make that work. And then, of course, the other one, it's buddy function, so cosecant kx, cotangent kx. You know, we're going to have a minus sign, but the derivative of that is going to be cosecant kx divided by k, because there is no k in front of here, so to get rid of that multiplication of k, you got to divide by it over c, plus c. 8 e to the kx. Why do they use t? I don't know, I guess usually I'll erase it, but for some reason, I guess there is a reason for that, is they tend to like to use t here for the variable. And the reason why is because exponential functions are usually used to represent like population growths, or in our case, what we're looking at right now. So t tends to be over time, so that's why it's a t. Now, for instance, if I have, I want to know, like, what's the derivative with respect to t of e to the 7t, for instance? Well, you know that this is going to be equal to e to the 7t multiplied by 7. So that would be the derivative, but what I want is, I don't want a 7t here, I just want a 7t. So in order to get rid of that, if I put a 1 over 7 right here, I would have a 1 over 7 right here, so this would just be equal to e to the 7t. So again, that's why we have these 1 over k's in front, because it's going to get rid of that that chain rule thing that we have to do. You know, the derivative of e to the 7t is e to the 7t, and the derivative of the inside is 7. So this takes care of that chain rule inside. So the derivative of e to the kt is going to be equal to 1 over k e to the kt. Of course, plus c. 1 over x, 9. One over x. Well, the derivative of 1 over x is going to be equal to the natural log of the absolute value of x plus c. And x is not allowed to be 0. Okay, the reason why we have absolute values here is because you can't take the logarithm of negative numbers, and you can't take the logarithm of 0. So that's why this absolute value of x here is just to verify that this thing is actually a real number. I'm trying to remember what 10 was. I'm having to skip one of them. I think it's 10. So number 10 is 1 over the square root of 1 plus, not plus, minus k squared x squared, or the quantity kx being squared. This is going to be equal to 1 over k to take care of that times the sine inverse of kx plus c. So I don't have any stipulations on that. So we know that the derivative, the derivative of the sine inverse is at 1 over the square root of 1 minus x squared. So if I have a k here, I'm going to have a kx squared. You're going to have a kx squared. So that's why it's k squared x squared. I'll put it in here. I'll squish it in. 11. 1 over 1 plus k squared x squared. So if this is our function, and then our antiderivative. Well, the 1 over 1 plus x squared is going to be the tangent inverse of kx. 1 over k plus c. And then 13. So these are the ones I need you to memorize. A to the k, there should be a, whatever. A to the kx is going to be equal to a to the kx all over the natural log of a plus c. Oh, times 1 over k. I guess I don't have to write the 1. 1 over k is just going to put a k on the bottom. Plus c. So remember, with the derivative of this, the derivative of a to the kx would be a to the kx times the natural log of a. So when I'm taking the antiderivative, that's why we're divided by that natural log of a, and also divided by the k because of this. We have to do the inverse of what we expect to do. All right, now put this to practice. Example. Determine the antiderivative. So what I mean by that is a general antiderivative, so don't forget the plus c. So f of x is equal to x to the fourth. So its antiderivative, our capital F. So our solution, we'll put our solution over here. So our capital F of x is going to be equal to, well, if we look at the rule, what we have here is this is the inverse power rule. So I have x to the n, so what I have is I have n plus 1 divided by n plus 1. So if this says 4 here, over here, this is going to say 4 here and 4 here. So using that rule, this is going to be x to the 4 plus 1, all divided by 4 plus 1, plus c. So this is going to be equal to x to the 5th over 5, plus c. G of x is equal to 1 over root x. Well, in order to solve this, I see a power. I see x to the minus 1/2 power. So what it is just another one of these. So I know my capital F of x is just going to be a power rule. So this is x to the minus 1/2 plus 1 all over minus 1/2 plus 1 plus c. So this is going to be equal to minus 1/2 plus 1 is x to the 1/2 divided by 1/2 plus c. And we can make that look a lot better. Dividing by 1/2 is the same thing as multiplying by 2. And this is root x plus c. And the derivative of this is this. C. H of x is equal to the cosine of 3x. So when it comes to the inverse power rule, you guys are going to get really good at this. X to the 5th over 5, x to the 1/2 over 1/2, and so on. Now, most of these things come down to me just kind of asking myself, what function do I take the derivative of to get cosine? Well, I got this mislabeled. This should be capital G. If that's G, then this is capital G. So capital H of x, it's antiderivative. Well, the function I take the derivative of is the sine. So I know that this is going to be the sine of 3x. Now, if I take the derivative of this is going to be cosine of 3x times 3, but there's no 3 here. So to get rid of that 3, I'm going to have to go 1 over 3 plus c. I of x, all right. Sine of x over 4. So remember, this is the sine of 1/4 x. This is equal to the sine of 1/4 x. All right, so it's antiderivative, capital I of x. Well, the function I take the derivative of sine is going to be cosine. But the derivative of cosine is negative sine, so this is going to have to be a minus cosine of x over 4. Now, when I take the derivative of this, you're going to have, I'm going to have, 1/4 times x. When I take the derivative of the inside part, I'm going to have a multiplication of 1/4. So if I take the derivative, if I kind of work on this, well, the derivative of minus cosine is going to be equal to a minus sine of x over 4, right? So we're good there. But then I'm going to have to multiply by 1/4, so I'm going to have a 1/4 here. So I'm going to have a plus 1/4 sine, but I don't want a plus 1/4. So the way we get rid of this plus 1/4, the way we get rid of this 1/4 is put a 4 here, because then I'd have a 4 here now, right? So now we can see that this is actually the sine of x over 4. So we have to be careful. Like, if this is 3 over 1, then its coefficient is going to be 1 over 3. But if this is 1 over 4, then its coefficient is going to be 4 over 1. Another way to kind of look at that as well is you would have 1 divided by its coefficient, right? 1 divided by its coefficient, so that's why you can write it as minus 4 cosine of x over 4 plus c. J of x. E to the minus 3x. No, I didn't put it. Let's put a coefficient here. What if I say 5 times e to the minus 3x? Well, with derivatives and antiderivatives, your constant is still there. So I'm still going to have a 5 here. Now, when I take the derivative of this e to the 3x part, when I take the antiderivative e to the 3x part, I know it's going to be e to the minus 3x. Now I'm going to have to divide by its coefficient, so this is going to be 1 over minus 3. So what I'm going to get here is minus 5/3 e to the minus 3x plus c. So same thing here. If this was a 2x to the 4th, then this would be a 2 still. So this would be 2 over 5, for instance. So the coefficients are just constants, and they can be, and you know that they're not affected when it comes to antiderivatives. So the rules. Linearity rules. When you guys get into matrix theory or linear algebra, these things come up a lot, and they describe some kind of vector space. which is super cool. Take my class, it's fun. All right, so 1. Constant multiple. So if I have my function and then my general antiderivative, what this says is if I have k times f of x, then the antiderivative, this is kind of what I was kind of leading to, is that the k is still there. It's going to be k times the antiderivative of f of x plus c. 2. Now you might think, why is it not this? Why is it not that? Because the k is left alone, and the antiderivative of f of x is capital F of x plus c. Well, the reason why we don't put parentheses around there is because even if I distribute, this would be k times f of x and plus k times c. And c represents any constant. So k times c still represents any constant. So it's redundant. You don't need to write a multiplication of 2 unknown constants because it's still just an unknown constant. So that's why we don't do that. It's still just plus c. Okay, 2. Negative. I can't believe I can't believe they wrote this. Okay, so I'm going to start it, but I'm going to finish it because they wrote it there. Negative rule. Well, if it's negative f of x, well, it'll be negative f of x plus c. The reason why I think it's silly to write that is because this is just a special case of k being equal to -1. So not a new thing. It's already taken care of here. So I don't know why they defined a new thing. 3, sum and difference rule. What I have is if I have f of x plus g of x, if I'm going to take the antiderivative of this, well, we know the derivative of the sum is the sum of the derivatives. So the antiderivative of the sum is going to be the antiderivative, or the sum of the antiderivatives. Now, it works for plus, and it also works for minus. To be honest, I don't think you really need a second one for difference, because if it works for the sum and it works for the negative, then it works for the subtraction. So it's not really necessary to redefine it, but they want to. So there we go. So sum and difference rule. So these are essentially, I should say sum, and then let's say this is difference. So sum rule, and then the difference rule. All right. Definition. What we need is better notation instead of capital letters. Oh, we basically need a little bit more than that. Let me give you a background. So when I say like f of x is equal to x squared plus 4x minus 3, I know that that f prime of x is equal to 2x plus 4. Now we give actually a notation to this that we'd say that f of prime of x is quite literally the derivative of this thing. So really when we're talking about its operation, we're saying, well, the derivative with respect to x of this expression is equal to this expression. So we know we can write the derivative as a type of operation that we're taking the derivative of this thing. So what I want is I want some kind of notation like this. I need an antiderivative operator. So that's called the integral. In this case, the indefinite integral. Indefinite integral. I guess they capitalize it all, but there you go. Indefinite integral. Integrand. So the set of all antiderivatives of f is the indefinite integral. So this essentially is the indefinite integral. Now we say the set of all antiderivatives because since we say plus c, c is an infinite amount of constants, so really this is a set of functions. It's a family of functions where it vary in c's. So we say the antiderivative of f is the indefinite integral of f with respect to x. And the way we write that is the integral of f of x with respect to x. So this is our notation. This is our notation. So what we had before, the derivative notation is that thing, right? That's the derivative notation. This is the antiderivative notation. So this thing essentially undoes this, which is kind of cool, is we're going to get to something that looks like that. And this is going to just spit out f. It's going to be awesome. Okay, so talk about inverses soon enough. All right, so this is our notation for antiderivative. Now this symbol right here looks like a stretched out S, and there is a reason for it. It technically kind of represents a sum, and we'll see that in chapter 5.1 and 5.2. So the symbol, this symbol right here, is the integral sign. And the function f is the integrand. And x is the variable. This is the variable of integration. So this kind of says a lot. So we say, when you look at this notation right here, let me just make it big again. So to kind of show you what they're talking about, is we have something that looks like this. So this is the integral of f of x. I know it's big, it doesn't have to be that large, dx. Now this is our integral sign. I could spell it nicely, would be great. Integral sign. Now this is our integrand. And then this right here tells us that x is the variable of integration. Now it might seem a little redundant to claim that x is the variable of integration since our functions only have a variable x, but when we move into multivariable calculus, when there's more than one of them, we need to describe what variable we're integrating with respect to. So it does become useful later. So don't just do this. You can't just do that because that's not a thing. What am I integrating with respect to? Because if you're integrating with respect to t, there's no t's, so this is just itself. So we have to be careful. All right. So for like our previous examples, for instance, what we could have done is, if I'm asking what is the integral of x to the fourth dx, well, we know that this is equal to x to the 5 over 5 plus c. So now we have some kind of operator. So instead of just saying find the antiderivative of x to the fourth, I can write it this way. This technically says find the antiderivative of x to the fourth. Or if I want, the antiderivative of the cosine of 3x with respect to x, you know that this is going to be equal to 1/3 times the sine of 3x plus c. So now we have an operator. Oh, and I can rewrite my rules too. So restating the rules, What we know is the constant multiple can be written like this. I can have the integral of k times f of x dx is equal to k times the integral of f of x dx. That what we can do is we can just pull out constants. That constants are preserved. The sign or the negative rule. That the integral of minus f of x dx is equal to minus the integral of f of x dx. That negative sign is conserved. 3 sum rule is the integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. So the integral of the sum is the sum of the integrals. The antiderivative of the sum is the sum of the antiderivatives. And then your difference rule is the integral of f of x plus, not plus, but minus g of x is equal to the integral of f of x dx minus the integral of g of x dx. All right, so that's that. So what we're going to do is we're going to evaluate our antiderivatives, and like an example is evaluate. And this is going to kind of move us to why these rules are kind of useful. So if I want to say what is the antiderivative of 6 minus 5x dx, well, what we know is the antiderivative of 6. Now, just to kind of show you that that 6 is the same thing as 6 times x to the 0. So its antiderivative is going to be 6, and I'm going to have x to the 1 over 1. So that's why we get 6x. So really it is a power rule. But we know that what do you take the derivative of? What do you take the derivative of to get 6x? So the derivative of 6x is equal to 6. So the way we can use our rules is this is the antiderivative of 6 with respect to x minus the antiderivative of minus 5 times the antiderivative of x with respect to x. So kind of using all those rules in concert. So I might have been a little fast with that. So the derivative of the difference is the difference of the derivatives. Now, what we can also do is we can pull out constants. So this is the derivative of 6 with respect to x minus 5 times the antiderivative of x with respect to x. So this is going to be equal to 6x. This is going to be equal to 5 times x squared over 2. And then, of course, plus c. Now, do we have to write all this? Heavens no. The antiderivative of this is this. And these rules allow us to take the derivatives of sums and difference and signs and constants kind of the way we were doing them before when it comes to derivatives. Like all these technically are just inherited from the derivatives. And they're inherited because they're a limit, and you'll soon understand that an antiderivative is also a form of a limit. So B, the integral of the square root of x plus 2 times e to the 3x plus 5 dx. So take the antiderivative of this. So what I know is that this is going to be, I can just take the antiderivative of each one of these. The antiderivative of that plus 2 times the antiderivative of this with respect to x plus the antiderivative of 5 with respect to x. So I know I can just take their antiderivative separately. So this is going to be equal to x. Well, adding 1 to this is going to be 3 halves. Remember, it's 1/2 plus 1 all over 3 halves. Plus 2 times, well, the antiderivative of this is going to be 1/3 e to the 3x. Remember, with derivatives, you'd be multiplying by 3. With antiderivatives, you'd be divided by it. And the antiderivative of 5 is 5x, and don't forget your c. So what I get here is divided by 3 halves is the same thing as multiplied by 2/3. So this is 2x to the 3 halves over 3 plus 2/3 e to the 3x plus 5x plus c. Now we have to be careful. There is no antiderivative rule for products. So, well, there eventually kind of is, but it's not. It's messy. It's quite messy. So there's no real general rule for it. It works for some of them and not for others. So what we'll learn is taking antiderivatives is much more complicated than taking derivatives. So what we can do is we can do sum and difference. We're allowed to do that, and we can pull out constants. So when it comes to antiderivatives, the easiest thing to do if you have the antiderivative of a product is multiply first, derivative second. So that's what I'm going to do. So this is going to be equal to the integral of x squared minus 3x plus 2x is minus x, and then minus 6 dx. So we're going to multiply first, we're going to integrate second. Remember doing that when we were using the product rule when it was first introduced in for derivatives is, you could do the product rule first, which is take the derivative first, simplify second, or you can multiply first and then take the derivative, and we got the same thing. So since there's no rule for products, multiply first, antiderivative second. So this is going to be x cubed over 3 minus x squared over 2 minus 6x plus c. All right. So same exact idea as with the other products. There's no product rule for there's no nice product rule for integrals. Same thing with quotient. There's no quotient rule for integrals. So what we're going to do is we're going to divide first and we're going to integrate second. So let's do our division. Well, this is going to be 4 over t cubed plus t to the 1/2 all over t cubed dt. Now I'm not done dividing, so this is going to be the integral of 4t to the minus 3, so I can write that as a power. And then when you do this, I'm going to have 1/2 minus 3. I'm going to subtract the powers, so this is 1/2 minus 6 over 2. So this is minus 5/2. So I can rewrite this as plus t to the minus 5/2 dt. So now using the inverse power rule, this is going to be 4. I'm gonna pull out the constant. You take t, you're going to go minus 3 plus 1 all over minus 3 plus 1. So that's the inverse power rule. And the same thing here, plus this is going to be equal to t to the minus 5/2 plus 1 all over minus 5/2 plus 1. And then, of course, plus c. Now, I know you can do these things in your head. I just want to write it out. So this is going to be 4 t to the minus 2 all over minus 2 plus... Well, this is the same thing as 2 over 2. So this is 5 to the minus 5/2 plus 2 over 2 is going to be minus 3/2 all over minus 3/2 and plus c. So finally, simplifying everything, 4 divided by negative 2 is minus 2 over t squared, because that's t to the minus 2. This is going to be minus 2/3 t to the 3/2. So this is minus 2 over the 3's in the bottom. And this is going to be t to the 3/2 down here, plus c. So just like we were doing before with derivatives, antiderivatives, I want the same thing. I want positive powers and simplify. One more division. Yeah, I can live with that. All right, so we're going to take the antiderivative here and with respect to x. kind of jumping the gun with one of these, but I want to do it anyway. So what we first have to do is we have to divide first. So in order to do this division, I'm going to use synthetic division. So you put the 0 of the denominator in the box, and then you do the coefficients. So 1, minus 3, and 2. Now drop down the 1 and multiply. 1 times 1 is 1, so this gives us minus 2. Ooh, I didn't want this. Of course it divides. Whatever. 1 times minus 2, so this is going to be equal to 0. So what we get here is this is the same thing as the integral of x minus 2. So this is going to be equal to x squared over 2 minus 2x plus c. What would have happened if we had a something left over? So f of x is equal to x cubed minus 5x squared plus x minus 3, and I'm going to go all over x plus 2. So, my bad, I want to do this instead. I want to find the antiderivative. Okay, so what we're going to do is we're going to divide first. So, using the box, negative 2 goes in here, and then 1, and then minus 5, and then 1, and then minus 3, and then we do our division. So drop down the 1. This is going to give us minus 2, so minus 7. 14, so this is going to be 15. Minus 30, so I have negative 33. So this is equal to the integral of, well, x squared minus 7x plus 15 plus a negative 33 all over x minus 2. X plus 2. Now we know that the derivative of the sum is the sum of the derivatives, so I'm just going to take the derivative of each one of these things. So this is going to be equal to x squared over 2. This is going to be minus 7, oh, sorry, not x squared over 2, but x cubed over 3 I have to add. So x cubed over 3 minus 7x squared over 2 plus 15x. And what I'm going to do is I'm going to pull out that negative 33, and I'm going to take the derivative, so that's minus 33 times 1 over x plus 2. That's what I have right there. So this looks like a lot like 1 over x, so you'll notice that this is the natural log of x plus 2. So we do have to be careful to make sure that this works. Let's take the derivative of this just to check it. Because what's funny is if it's not linear in the bottom, it's not a logarithm. So since this is a linear denominator, it is. So the natural log of 1 over x plus 2 would be 1 over 1 plus x plus 2. So this actually does work. And then I have plus c. So differential equations, what we did before, but we're going to have a lot more form now. It's going to be a lot more sophisticated as far as our notation. But it's no different than what we did before. So it's, if you understand the other one, it's nice. So example, I want us to solve the derivative with respect to y of x is equal to 10 minus x, where y of 0 is equal to negative 1. Now, I gave you something very similar before. What I did is I said that, how did I write this? I said find the antiderivative of y, which is equal to 10 minus x, given, I think I call this f, I think I call it f, of f, which is equal to 10 minus x, where capital F of 0 is equal to negative 1. Now this is essentially, this is the exact same problem. Like, I'm asking you to find the antiderivative of this such that that antiderivative goes to 0 comma negative 1. So we did a problem just like that. So just to tell you that it's no different. Now, our notation is going to change now. So our solution is, I know that I need to take the antiderivative of this, but the reason why is we are going to take this kind of idea right here. I have, this is the derivative of y. So I'm going to take the antiderivative of both sides. So what's kind of cool is the antiderivative of dy of y with respect to x. What's going to kind of happen here, and forgive me, this is the notation's kind of messy, and it's not technically how this works, but you can kind of see like those go away, right? So now I have the integral of dy, and the integral and that derivative is actually going to cancel, so this is just going to spit out y. Now I know this is on video, so I can't deny it, but this is kind of like a hand wavy version of this. But technically, the reason why this is the case is the antiderivative of the derivative of y. So what this is this is the antiderivative of the derivative, right? And that basically means it's just going to spit out the function. They are inverse operations, or at least as close as we can get. So kind of like the same idea as how do you get rid of a square root? Well, you square it. Are they inverses? They're close enough. The problem is square roots aren't 1 to 1. I mean, squares are not 1 to 1, so you have a little bit of inverse problems, but at least it's the closest we get. So same thing here. It's not exactly the inverse, but it's the best we got. So what I'm going to do is I'm going to take the antiderivative of both sides. I'm going to take the antiderivative of this side, and I'm also going to take the antiderivative of this side. So when you're taking the antiderivative of the derivative, you're going to get y back for this. So this is going to be equal to here. So when I ask you to solve an initial value problem, what I'm looking for is I'm looking for a function whose derivative is 10 minus x, and that function goes through 0, negative 1. So this is how it's done. We just take the antiderivative of both sides. So this is going to be equal to 10x minus x squared plus c. So this so far is our function. The derivative of this is this. We've got that. But I still need it to go through 0, negative 1. So that's what I'm going to do. Now I'm going to find c. So y of 0 is equal to negative 1. So that means y is equal to negative 1 when you plug in x is equal to 0. So 10 times 0 minus 0 squared plus c. So this says c is equal to negative 1. So therefore, the equation that has these two properties is y is equal to 10x minus x squared minus 1. All right, so let's take it one more. Same problem, but we're going to go, it's going to have an extra step. So solve the initial value problem, so IVP. So the second derivative of y with respect to x is equal to 2 minus 6x. And also y prime of 0 is equal to 2, and y of 0 is equal to, I don't know, 7. Negative 7, whatever. All right, so figure this out. What I need to do is I have a second derivative. So last time I had the first derivative, so I had to take the antiderivative once. Well, now that I have a second derivative, I need to take the antiderivative twice. Well, I'm going to do it the first time and then use this, and then I'm going to do it the second time and I'm going to use this, okay? So when I take the antiderivative of this thing, solution. So the antiderivative of the second derivative, so if I only take one antiderivative, what you can see is that this dx is going to handle one of those dx's, and this integral is only going to handle one of the d's. And this is going to be anti of 2 minus 6x with respect to x. So what you're going to get here is you're just going to get the first derivative back. So the antiderivative of the second derivative is the first derivative, and then we take the antiderivative of this side, which happens to be equal to, is going to be equal to 2x minus 3x squared plus c. Now what I'm going to do is I'm going to go ahead and find c. I'm going to call this c1. I'm going to find c1. So in order to find C1, I'm going to use this right here. So this is going to go into here. Okay, and we're going to do the work right here. So when I plug in 0, its derivative is going to be equal to 2. So the derivative is going to be equal to 2 because that's what y prime is. And I'm going to plug in 0 here. So 2 times 0 minus 3 times 0 squared plus C1. So that means C1 is equal to 2. So to find the constant for the first derivative, you're going to use the first derivative. So now I have dy dx is going to be equal to 2x minus 3x squared plus 2. Now I need to do it again. I'm going to take the antiderivative. So I have to find the function. So the antiderivative of the derivative with respect to x, antiderivative of this side, is going to give me this is going to give me, well, x squared over 2. So this is going to give me x squared. This is going to be x cubed over 3, so it's going to cancel that 3, so this will be x cubed, plus 2x plus c2. Right. So in order to find c2, I'm going to use this one. So we're going to plug that into here, and it's going to give us this. So remember that this is y, right? So y is equal to negative 7 when x is equal to 0. So it means C2 is equal to negative 7. So our final answer is y is equal to x squared minus x cubed plus 2x minus 7. One more of those because they're fun. I'm going to make it up, so hopefully I don't get any errors here. So the first derivative is equal to minus cosecant squared of x over 2. And I don't want to do pi over. And y of pi over 4 is equal to 7. All right, hope I don't regret this. All right, so what I'm going to do is our solution here is we're going to take the antiderivative of the derivative with respect to x, and I'm going to take the antiderivative of this thing as well. Now what I know is in order to get the cosecant squared, I know it comes from the cotangent. So in this case, it's going to be equal to the positive cotangent of x over 2. And the reason why is because the derivative of the cotangent is the minus cosecant, so we're good here. Now I still have to divide by 1/2, which is the same thing as multiplying by 2, plus c. So that's why. Now what I'm going to do is I'm going to plug in pi over 4 to find c. So y of pi over 4, I'm going to erase this. So when I plug in pi over 4, I'm going to change this. I'm going to make this pi over 2 so it's easier to do. Which you could do that, don't you? So I'm going to plug in pi over 2. So this is going to be, when I plug in pi over 2 into the x value, what I'm going to get is, this is going to be the cotangent of, so this is 2 times the cotangent of pi over 4 plus c, and that gives you 7 when you do that. So I know that the cotangent of pi over 4 is equal to 1, because it's root 2 over 2 divided by root 2 over 2. So this is just going to turn out to be 1, so 7 is going to be equal to 2 plus c, which means c is equal to 5. So therefore our equation is y is equal to 2 times the cotangent of x over 2 plus 5. And that's it. That's that section. Done with chapter 4.